Good evening, Dr. John Casani. We really appreciate you making time in your schedule to attend today. To all of you, it's a great honor that Dr. John Casani is with us today. Allow me to officially announce the start of the forum. 各位老师、同学，大家早安！我是今天的主持人，民传大学的全胜利。在今天这场特别的演讲进行方式会比较特别，将会有3位主持人主持节目，分别是我，还有节目主办人刘登凯博士，以及 Q&A 主持人 Iris 从洛杉矶连线。麻烦各个学校与各位同学在更换主持人的时候，轮流将各个主持人定选到 Webex 的舞台中央，和演讲人在同一个画面。首先欢迎在场各位老师同学来参加由连结台湾好奇学生大哉问、大同大学、辅英科技大学、民传大学联合主办的好奇学生大哉问线上演讲。谢谢现在线上参与的各间学校，其中包括台湾大学、成功大学、中央大学、淡江大学、逢甲大学、大同大学及 NSPO 等等的热烈响应。仍有其他有效未能详尽，谢谢各方学校的参与。我们的宗旨呢是建立一个平台，邀请海内外专业人士，透过每月1次的专业演讲，将他们的经验知识与大学生们分享。希望同学们能将这些书本上学习不到的知识，直接运用在将来寻找工作或求学深造方面。我们的演讲嘉宾来自4方，包括美国加州、
这是老外，
台湾和日本，
绝对会讲英语，你仔细听吧。
活动目前规划是每个月的第3个星期五早上10点10分到11点45分，由线上视讯的方式呈现。希望各位同学们能够及时听到好的演讲，并且大胆地在视讯中直接与嘉宾对话。今年元月起，为了加强学生与嘉宾互动，并增加同学们的领导与组织能力，这个系列将改由学生主持。欢迎有兴趣参加团队的同学不要害羞，随时大方的与我们联系加入团队。其实呢，会没有兴趣的事物，大多都是因为没有好好认识过，才会感觉没兴趣。所以千万不要错过任何机会，机会等着你来实现。另外呢，为了鼓励学生参与演讲及筹备工作，我们制定了许多鼓励的办法，分别是鼓励学生在演讲前规划演讲方向，举办一场自己想听的演讲，当好一位好奇学生，在演讲后大胆提问，参与工作团队学习合作能力。希望在好奇学生大哉问的演讲当中，所有学生在听取前辈向我们阐述的言谈之后，能够感受到前辈们致力于学生学习的热忱，激发学生的想法，让学生尝试思考自己的未来。本次演讲主题是由 NASA 探测计划主持人 Casani 博士为我们带来的美国太空探险金色年华袐辛并兼谈太空船之诞生。那么接下来有请我们的节目主办人刘登凯博士为同学们介绍奖金的部分，有请刘博士。
大家好，我是刘登凯，欢迎大家来和这个跟这个 Iris 一起来探讨太空探险这个议题。那为了鼓励同学们发问，从这个发问当中呢来求这个进步，成就非凡未来。我们的奖励的办法有2个办法，一个办法是在演讲之前呢，我们就请同学来发问。那这个我们在当中呢选出一共3名来，第1名是1000块钱，第2名是500块钱，第3名是300块钱。同样的，第2部分呢就在现场，当我们的主讲人讲完了以后呢，我们后面有这个提问跟回答的问题，我们也同样选出3名来，第1名是1000，第2名是500，第3名是300块钱。我期待同学们的这个智慧在这里。如果你们找不到答案的话，我也希望你们继续努力找答案，找到答案为止。好，我把现场交回我们的主持人。
谢谢刘博士的说明。接着在这里跟各位同学讲解一下节目流程。在结束演讲后呢，我们会直接开始50分钟的 Q&A 环节。如果对我们演讲者精彩的演讲有任何疑问，欢迎利用我们身后的 QR code 发送问题。那我们呢会选择3位问得好的问题获得好奇学生奖励金。 以及在公布得奖同学的时候，我们也会颁奖给演讲前提问的同学们。我们非常鼓励同学们于活动开始前就上网查找资料。这次的问题呢，必须包含 Dr. John Casani 的技术领域和团队合作等层面发想来询问问题。本演讲的宗旨一直都是希望学生大胆提问，成就非凡未来，所以我们愿意于事前提问这方面提供丰富的奖项，希望各位同学踊跃参与。这里再多讲几句节目流程。在结束演讲后，我们会直接开始50分钟的 Q&A 活动环节。那我们会选择3位问得好的问题获得好奇学生奖励金。那我们那就是在现场提问的时候，欢迎各位同学大胆的踊跃参与。谢谢。再来就是，请各位将问卷送出前，一定要再三确认你的联络资讯，不然结束后公布得奖名单，联络不到同学会很可惜。那么接下来有请大同大学的何校长为现在与会的同学们介绍今天的演讲嘉宾，有请何校长。
各位同学好，唯一呢，我到旁边来。OK， Dr. John Casani, a very honored to have you today to give us a speech to our students in Taiwan. And allow me to spend a few minutes to introduce you, and also since Iris is next to you, so introduce both of you in Chinese. OK， 各位同学各位老师大家好。那今天非常高兴，我们有这个美国的这个太空传奇人物John Casani 来帮我们这个演讲。那 John Casani 本身的这个生涯就是整个美国太空探险的这个历史。他做过哪些事情呢？在过去的40年，他这个负责了这个发射了这个 Voyager 就航海家号。航海家号现在已经离开太阳系，仍然呢在传回讯息。他也主持了这个 Galileo， 就是那个伽利略号这个计划呢，就是到木星去探险。还有这个 Cassini 这个计划主持人呢，就是到土星去探险。等等，还有包括这个调查这个2000年 JPL 到火星这个登陆探测器失去的这个联系的这个调查等等。也就是说，他的这个生涯就是包含了整个美国的太空探险，这个是非常难得的机会这个请大家想好你的问题，等一下尽量的这个提问他也得到了这个太空总署的特别服务奖，那是给非官员的最高荣誉，得到宾州大学、罗马大学的荣誉博士。也得到这个国家航空和太空博物馆的终身成就表这是非常难得，请大家这个期待好好的看今天的这个演讲那提出最好的问题。那接着呢，我介绍这个 Iris 这个 Iris 这个以共在这个 Connecting Taiwan 也做过一次演讲。Yeah, I'm introducing Iris. Iris also gave us a talk a few years ago. Explain how he transformed herself from a medical technology to music technology, totally different major. OK， 那 Iris 呢？她在几年前也曾经这个在 Connecting Taiwan 演讲过，那也欢迎同学对她如果有兴趣的话，她的演讲有兴趣的话，可以再到前面去找档案。那 Iris 呢，就是叫做吴彩怡，她是一个创新音效公司的 MVideo 的这个创办人他的这个毕业的学校是台北医学大学Medical Technology， 就是医技系。那他的后来呢，他也当过这个吉他老师他到美国纽约大学就读了这个 Music Technology Music Technology， 我想可能是填志愿填错了，申请学校字写错了都是 Music 跟这个 Medtech 写错了他就去那边这个读音乐，变成一个音乐特效专家特效专家。他在2019年他成立这个 MVideo， 在2019年得到好莱坞专业协会的这个杰出工程技术奖。但是这个公司他得这个奖是那个奖有史以来给过最年轻的公司，而且是最小的公司，好像只有4个人吧非常小的一个公司。然后他在这个音乐特效上面有非常这个杰出的成就也是他是also在这个 board manager， 在这个
Society of Motion Picture and Television Engineering Hollywood， 等等，他的这个在音乐的成就非常大，也跟同学一个启发，就是他从这个一技可以跨到音乐音乐科技，而且是工程的那也希望大家有兴趣回去可以看以前的这个录影。And so 我现在就把这个主持交给 Iris。So Iris，it's your time。
谢谢校长。大家好，我是 Iris， 然后今天有跟 John 在这里。You want to say hi to everyone?
Hi.
So now
Nice to be here.
I'm going to introduce you some more and how cool you are in Mandarin. So just smile. 就是刚刚那个校长稍微介绍一下 John， 但是我想要自己再加一些东西。像刚刚他有说他得了一个奖是美国太空博物馆的终身成就奖。那个时候我在看他的那个 list 的时候，我会觉得这个奖到底有什么帅？就是个奖在博物馆。就后来才发现这个奖超级厉害。然后就其他得奖的人，就比如说像是设计波音747的人啊，或是那个 Neil Armstrong， 就是那个我的一小步就是人类的一大步的那个阿姆斯壮，就是得这些奖的人。然后像团队，像是设计哈勃望远镜团队也是 SpaceX 的团队，去年也得。然后他也是其中一个得奖者，所以这个真的超级厉害。然后大家会知道他，就是我觉得很有名，就是 Voyager 射了2台，现在都已经在太阳系之外了。我那时候第一次遇到他的时候，我会觉得这个人超厉害，他是飞离宇宙最远的男人。然后他就会跟我说，我没有飞离太阳系最远，是我做出来的东西飞最远。这是理科男的思考。但我觉得这件事情真的是非常酷，就是 Voyager 它花了35年嘛，2012年飞出太阳系，然后今年已经44年了，然后到现在还在传讯息回来。这件事情光想一想就觉得超级厉害，因为我的 iPhone 那2年就不能用了，但是它这个东西到了40几年，到现在还在传讯息回来。那 Voyager 有一些还蛮有名的东西，你们可以去查查看。就比如说，他在1990年的时候有一个非常有名的照片，叫做 The Pale Blue Dot。We're talking about a famous photo of Voyager sit back。然后那张照片是地球最远的照片。然后 Voyager 照那张照片的时候就把相机关掉了。但是这个照片真的是会觉得哇，超级厉害。然后他到现在，比如说今年5月的时候啊 ，Voyager 还传了一些他录到的，就是星际介质的一些嗡嗡声回来。然后，如果大家有兴趣的话，就其实 NASA 在它的 SoundCloud 的 channel 里面有把这些太空船录到的一些神秘声音全部都上传上去。所以，如果大家想要在星际介质的嗡嗡中睡觉的话，大家可以去听听看。然后，我们先讲一下就是 Voyager 好了，大家应该有听过 Voyager 的事情，可是大家知不知道 Voyager 上面有一张金唱片？然后我觉得金唱片是一个很酷的东西，它其实不是我们第一次尝试把我们的存在告诉外星人。在之前 Pioneer 上其实有一个小金版，然后在 Voyager 上面升级，它现在除了照片还有音乐，然后我们有一个小小的影片，然后大家先看一下，你可以帮我放一下那个 Voyager 影片那个音乐影片。We're playing the good record video。
麻烦等我一下下。
好，在等的时候我要继续讲了，就是那个金唱片真的很酷，就是在大概那个时段，很多电影里面都会有一些 reference。就是我不知道，我小时候看的，就是有一个叫做《百兽战队》，就是变形金刚变成动物的版本。然后，sorry。
The history of the record is that I asked Carl Sagan at one point in the project if he would work to develop some sort of a message or some kind of a plaque that we could put on the Voyager spacecraft to communicate to whoever might ever find it. And he said, here's what I want to do. I want to put a record on, which won't weigh any more than a plaque, and we could put on that record music. The record was mounted on the outside of the spacecraft, but because it would be exposed to interplanetary dust or interstellar dust, over a period of millions or billions of years, it could have a corrosive or erosive effect on the record. So we wanted to prevent that from deteriorating the grooves in the record, so we put a cover plate over it. The presence of that cover plate was taken by Carl and his team, inscribing on the cover plate a couple of things. First of all, they inscribed in directions on how to play the record. Now, the other thing that's on the record is the location of the Earth in respect to our galaxy, and that's represented by this pattern. At the center is the Earth, and these radial lines going out in these in different directions are directions to pulsars. Now, the possibility of it being found is so close to zero, it's almost impossible, but it's not impossible. There's a very small chance that some race of creatures could come across it in the future.
嗯，刚刚那个就是关于金唱片的一个影片，我们再回去讲那个百兽战队。就是金唱片这件事情在那个时候真的超红，所以很多电影里面都会有这个的 reference。像他们百兽战队就是一大堆变形金刚，他们为了要找一个叫做金盘的东西，因为那个金盘上面记录了地球的位置，然后这个就是这个金唱片里面做的事情，他告诉了外星人就是可能会找到我们的人，我们是什么样子的人，我们的坐标在哪里，然后我们的生活是什么样子。So just talking to them about why do we have this gold record. So gold record is to tell people out there, or species out there, that who we are,
Yep.
where we are, and what we are doing.
Yep.
So speaking of that, do you believe in aliens?
Do I believe in aliens? Well, yes, I do believe in aliens. By aliens, I assume you mean some species living elsewhere in the universe that are intelligent and have technology and could be having conversations with each other. I believe there's aliens all over the universe.
Yeah.
Yes, I believe someplace else in the universe today, there are two people speaking in front of a camera to 240 students, having the same conversation that you and I are having. That's how common I think life is elsewhere in the universe. Does that make sense?
Yes. Have you heard what Stephen Hawking said?
Yeah.
So Stephen Hawking warned us because we know so little about aliens, so we should be really careful about going out and searching for the alien. Yet we send them where we are and the location. And like, why do you decide to do that in the first place?
Well, I think I don't know if I can answer that question in the first place, but why not? I don't think there's any danger personally, and I think many people agree with this too, that will be invaded by the aliens and subjugated to them in some way. I don't think we'll ever have any direct contact with them. It's kind of like picking up a book that was written 2,000 years ago by a Roman or Greek scholar. We'll never have a conversation with them because that book was written 2,000 years ago. So whatever we would say, they wouldn't hear about it for 2,000 years. But we still can learn a lot from one-way conversations. And I think that's all we're ever likely to have with aliens.
Speaking of that, why do we do space exploration anyway? Why do you want to explore space?
Well, I think it's all about understanding what the science behind everything. Why does How did space start? How did we have all these stars that we see in the sky? Why is it that at least one of them has a planet with life on it? Where did the life come from? How did it start? All those questions. And how did the universe evolve? How did our solar system evolve? These are scientific questions, and there's people have a natural curiosity about them, and that's why why do any science? Because science leads to technology, and technology enables better science to be done. So the two work together. You know, I'm not a scientist. I'm an engineer, but I make things, and then other engineers make things that allow scientists to do more work. Do you think that we'll ever know everything there is to know about science, and the search for new knowledge will no longer be interesting because everything that can be known is known?
No, they're so limited.
I don't think that could ever happen. Well, when that happens, then we don't have to go in space anymore.
I think the curiosity is just like human nature.
Yes, it is human nature. We all want to know where we came from. You know, how did we get here? Why are we here? Those are philosophical, scientific, and questions that can only be answered with technology.
Okay, and speaking of all these missions you've done, so for Voyagers, a lot of people say it's the most significant mission of the whole U.S. space exploration history, even in the human space history, because it's the first one that's out of the solar system.
Right.
And what do you think? Is this your favorite mission? Or what's significant about Voyager?
Well, Voyager is my favorite mission. I have to admit that. But it's like people often ask me that question: what mission do you love the best? And my answer usually is, well, do you have children? Yes. Which child do you love the best? And they can't answer that, or they won't. And yeah, and so I mean, it's sort of the same thing. I love each of those missions that I've worked on. I've worked on a lot more than just the three that we've talked about. Have different attributes. There's things different about them that endear me to them, or that I feel proud of having been associated with. But the thing about Voyager, it was the first time, as you said, that we ever sent a spacecraft outside our solar system. It's there's two of them. They were both launched about 44 years ago, and they're still working, and they'll probably be working for another maybe 10 or 15 years. That's when the power supplies will be exhausted. But physical presence, they'll be there forever, for billions of years. They'll be silent messengers, broadcasting to our galaxy the presence of we as a species. That's something to think about.
That's pretty romantic.
Pardon?
I think that's pretty romantic. My standpoint of view. John 他加入 JPL 大概有60几年了吧，差不多。You're saying it's almost 60-something year you joined JPL, right?
I didn't understand that. No, what did it say it again?
Oh, I said you joined JPL for 60-something years.
Oh, I joined JPL in 1956. I think it was.
It's about, yeah. 所以这就是美国太空探险的活历史。他在刚加入 JPL 的时候，就是 JPL 才刚刚开始准备从做火箭变成做太空船，所以基本上 John 就是帮忙 lay out 了整个就是这些 project 该怎么做啊，然后这些 foundation 都是他建立起来的。然后讲到了这些太空船到底该怎么样建造，我们有另外一个 video。然后想让大家看一下一些简单的怎么样做太空船的一些步骤。放一下。
So what were you doing? You were
to create the clip for the JPL tool, like how a spacecraft were born.
Oh, okay. That's what we're going to show them next. Is that what you're saying? Okay.
That's the thing we're going to show you now.
Oh.
JPL machine shop now, fabrication area. This is where most of the metal parts, the large ones at least, that comprise the spacecraft are manufactured. A lot of the stuff we send out to local machine shops, but the bigger and the complicated pieces are done here. Most of these machines have numerically controlled spindles, all computer operated. The drawings frequently come right out of the design room as electronic code and are programmed into the machines, and the machines build the part. We call it art to part, and it's an innovation that's been started maybe 15 or 20 years ago. And all of the major parts for Galileo, Cassini, and Voyager came through this shop here. Before we put all the spacecraft components together, the subsystems like the radio subsystem or the power subsystem, we bring those subsystems in here and we put them through testing. So we have capability, different size chambers for different size pieces of equipment. 10-foot chamber, 7-foot chamber, 4-foot chamber, 3-foot chamber, all for thermal vac. In space, there's no pressure. Space is almost total vacuum, so that we try and get to as close to total vacuum as we can with these chambers. Normally, the operating range in space is pretty close to room temperature, but for testing and qualification, we have to take it to a much lower temperature and to a much higher temperature. And that's what these chambers are used for. So they can take it up to 125 degrees centigrade and down below, well below zero. So now we're in the SAF, Spacecraft Assembly Facility. This is where we put the spacecraft together. And behind those windows over there, you can see, is where the electrical test equipment is. When we're testing the spacecraft, the people who are doing the testing and the equipment that they use for testing are behind that wall. That's one of the technicians that you can see down there in this bunny suit, we call it. It's a model, he doesn't move, but it shows you the scale of things at least. And over there is a fixture that's called a turnover fixture. You can mount the spacecraft on that ring in the center, and then the whole thing can be rotated about this axis. You see the motor on the end here, so the spacecraft can be put horizontal or vertical, and it has to be in different positions depending on what the actual test is. On the wall over there are some plaques of the different missions that have been assembled and tested here. So the 30 spacecraft represented there. I think the first spacecraft that went through here was probably, was one of the early Rangers. The very first Rangers were tested in a hangar that we used to build launch vehicles in, and this building was built in 1960 or 61. We're about to go into the vibration test facility. That's where we shake the spacecraft. You'll see that in a minute. But right now we have to put on these suits and go through an airlock, take an air shower to brush the extra dirt and hair off us before we can go in there and possibly contaminate the facility. We've got a couple of shaker tables here. A shaker table is a table that can move under the influence of a big electromagnetic coil. Put voltage and the frequency in there, and this table moves back and forth. In the case of Voyager or Galileo or Cassini, the whole spacecraft would be mounted to that table with an adapter fixture, and then this machine would turn on, and it would shake the spacecraft violently, in that direction. To test it in another direction, we'd have to turn the spacecraft and get the shake in the other direction. It's also possible to tip that whole thing, shaker upright, and shake it in the up and down direction. Standing outside of the 25-foot simulator. We'll go inside in a second, go through that door there. That's just a personal access door. Move the spacecraft in there. There's a much larger door that small door is in. It's about 12 or 13 feet wide, 25 feet high, and we could take the whole spacecraft, roll it in through that big door. Then the door would roll from the right to the left here and go up into the chamber and be sealed up. Right now we're standing in the middle of the 25-foot solar thermal vacuum simulator at JPL. Every major spacecraft that we've ever built or flown has been tested in this facility, including Galileo, Voyager, and Cassini. This chamber can be evacuated to simulate the vacuum in outer space, It can be irradiated with artificial sunlight. We can create a sunlight that's equivalent to more than the sunlight you would see at Venus, but not as much as Mercury. And then of course it can go all the way out to Jupiter, Saturn, Uranus, and Neptune because the sun gets very, very dim. Well, right now we're in the Mission Control Center at the JPL Spaceflight Operations Facility. It's from this area here that all the spacecraft that we have flying, there's a lot of them, are controlled. The room that we're standing in now is the main room for controlling the DSN antennas that are situated around the world, tracking each of the spacecraft. And also the spacecraft operations, where people actually controlling the operation of the spacecraft also are in this facility. This room was used for Voyager, for Galileo and Cassini, and for every spacecraft JPL has ever operated. It's been upgraded several times. It was built, I think, around early 60s, I think this was built. And it was built specifically for this purpose. It was the first facility of its kind. And I believe it's a national heritage location because of that. So I don't think we can tear it down, even if we wanted to, which we don't.
So that's the clips about a brief steps on how a spacecraft was born. So let's go into some technical question we got from our student.
Okay.
So the first one will be from Qiu Xiuze. So the question would be Voyager 1 and both Voyager 1 and 2, they are far, far away from our Earth, but they are still sending data back.
Yes.
How is that possible? And what are the technology behind?
Well, fundamentally, it's there's nothing new about the technology. It's we do it by radio. We send signals to the spacecraft by radio, and the spacecraft sends information back to us by radio. It's radio. It's just like it's just like a radio. Turn on the radio and listen to the news. Where does that come from? Well, there was a station with a person speaking into a microphone, and the microphone signal goes into a transmitter system and it's converted into a radio wave, which is broadcast out from the antenna, goes out all over the place. And some different places, there's a little antenna that can intercept part of that signal. You don't see the whole thing. And then it gets converted back into sound. So it's just a radio system. That's all it is. The challenge is that it's not just like sending a radio signal from Los Angeles to San Diego or Los Angeles to New York City. It's a radio signal that's going from one star to another, almost. Far. Yeah, and so the radio transmission seems like instantaneous to us because it's really very, very fast. It travels at the speed of light, which is less than a blink of an eye. But the further you get apart, the longer it takes that signal, even moving at the speed of light, to get there. For instance, the signal that we transmit from Earth to Voyager now, or from Voyager back to Earth, I'm not exactly sure, but I think it's on the order of an hour or maybe more, right? The closest star, other star to our own sun, is about 4.2 light years away, which means it's a radio transmitter signal that leaves the Earth today doesn't get to Alpha Centauri or whatever it is for over 4 years. And it'd be hard to drive a car if the kind of traffic light turned red and you were able to put your foot on the brake. Took 4 years, right? But we got to drive spacecraft that way. So that's that's the bigger problem. And it's not the fact that the signal has to travel such a long distance or takes such a long time.
It's the delay.
It's the delay.
How do you deal with the delay then?
Well, the spacecraft has to be designed to be smart enough to handle all the things that happen when they happen. And we send up, then we have the system designed so that it's pretty automated. It's like self-driving car, but it's a self-driving spacecraft. Or a rover working on the surface of Mars. So, we have to go from point A to point B with the rover. And we know where the rover is, it's at point A, so we don't drive it from A to B with steering commands from the Earth. We send the location that we want it to go to the spacecraft, to the rover. And then the rover takes over and steers itself to that location, avoiding obstacles, stopping, going around corners.
That's smart.
And so it takes a longer time to do it, but it would be impossible to try and do it with a
Real
transmission time of, say, round trip of half an hour or 45 minutes, which is what it is. It just couldn't react in time. But the spacecraft, if it's smart enough, can navigate and do that. And you only have to send it instructions in terms of the geo-coordinate system where you want it to be in 24 hours or 8 hours.
One of the questions from another student, Xiong Lin Kai. So when you design a spacecraft, what are some important factors you will consider? So you talk about the balance between the mass and the budget and the power, and what else? Or can you talk a bit more?
Well, the things that you have to consider are, first of all, the costs. There's only so much money, or the customer may say he doesn't want to spend that much money. That's a driving factor. Okay. Then there's the value that a customer wants from it, which can be expressed in terms of scientific data, measurements, you know, or resolving a certain issue of one kind or another. That's another thing. That comes from the customer, and the customer will arrive at that by putting out sort of an invitation to propose to the science community, saying, here's the general things that we're interested in. What do you guys out there in the science community think you can do? Tell us what information you need to collect and what kind of an instrument will be required to collect that information, and what will that instrument cost, and how much will it weigh, and how much power will it take. So the science community will come back with a bunch of different proposals, and the customer, NASA headquarters generally, will select one or a combination of ones. And so then that becomes an input, another variable that you've got to include in the equation. The size of the launch vehicle is another one. The customer will say, look, we have to use only this type of launch vehicle, you know, and there may be 3 or 4 types of launch vehicle, each one capable of launching a heavier spacecraft to the desired point, but maybe having a variation in cost, and it would have a variation in cost. So the other thing is, and it's power. How much power is all this going to require? That's an important thing. And the other thing is the environment. Where is this going? Is it going to go to the surface of Mars? Is it going to stay in orbit at Jupiter? Is it going to go out of the solar system and only be subject to cosmic rays and cosmic dust? You have to know what environment the design has to capture. And then it's just a question of turning the engineering crank and varying these parameters until you find something that closes, a solution that satisfies all those input conditions. And if you can't find it, then you go back to the customer and say, look, you know, we can do everything you wanted, but you know, it's going to cost too much, 2.5 times as much as you think you have. Or you can go back and say, we can do this, but not with that kind of launch vehicle. We need a bigger launch vehicle. Well, that's going to cost more money. You know, or you say, we could do that, but we can't return all the science, and we can't get it all back in the 5 years that you wanted us to finish this. It's going to take 10 years, and that's going to cost more money not to build the spacecraft, but to operate the spacecraft for another 5 years or whatever. So those things all have to be laid out in a project plan and have to be presented to the customer, and the customer either agrees or doesn't agree. And if the customer thinks he just didn't do it, they just, well, I'll go find somebody else that can do it. And if they can, we learn a lesson.
But going back to that design question, so you make all this design, you calculate everything in modeling, but how do you make sure it will work? Because like everything outside, there's a lot of unknown.
Yes.
So how do you make sure the design will work out there?
Well, there's really two questions. How do you make sure the design will work? And you said you put the tricky part in out there. So if you say, how do we know it can work? We design it with certain requirements. And if we design it right, then we can test it and see whether it meets those requirements. Now, if those requirements represent accurately enough what the conditions will be when the spacecraft gets there.
Question.
Yes.
So the requirement you are referring to are like the ones you said in the clips, that when you shake really hard, it won't fall apart. This is one of the requirements.
Well, see, there are 2 sets of environments that we talk about, and maybe we don't distinguish clearly enough. There's what we call the natural environments, and then the induced environments. The induced environments include the vibration that the spacecraft feels during the launch vehicle, okay, because that's not natural, it's there because we're launching it, you know. So there's environments like that. We can measure those. We've got a lot of launches, we know what that is. Acoustic environment, also very large sound that bounces off the outside of it. All of those things are induced environments, and we have a pretty good handle on what they are. We had built stuff that wasn't strong enough or hadn't considered all the induced environments, but we're sort of beyond that now. I think that pretty much is the thing. Then there's the natural environments. The natural environments are what it runs into just by where we send it. The surface of Mars or the surface of any planet that we want to land something on, we can consider a natural environment until we were able to characterize it. Once we get there, we can, you know, map it and see what the variation in rock sizes are, and how the density or softness of the soil varies from location to location. Then you can if you can specify that, then you can design to it, and you can recreate those conditions on the Earth and test it there. So again, you would validate it by test.
But first, you need to collect data.
Yes, you need to collect data, or you have to synthesize the information on the basis of scientific modeling. We say, this is what we know from a scientific point of view, and if that's true, then this ought to be the surface. Or, you know, what did we know about the surface of the moon? We didn't know before Apollo astronauts or surveyor went down there whether it was going to be like talcum powder and something landed on the surface of the moon 20 feet, 620 feet below the surface of talcum powder.
Yeah.
You know, so that was. But once we got there and measured what it's like, then design something to land there was not so hard. So it's the same thing. So
but for the things like Voyager, because it's so far away from the boundary of the solar system.
Yeah.
How do you know what happened outside of solar system?
We don't know what happened outside of the solar system, but from a theoretical basis, we know a lot about what happened inside the solar system. And you can say, you know, there are going to be charged particles, ions, which have come from other stars exploding billions of years ago and putting their debris out. And we're going to run into that. We know, for example, that the golden record, which we haven't talked about too much, will eventually feel the erosive effects of micrometeorite bombardment over billions of years. That you won't anything show up for a year, 10 years, 100, 1,000 years, but after a while, that continual bombardment of those micrometeorites and the continual exposure to ionized radiation will affect the surface characteristics of the spacecraft. And so we can't test for 1 million years or anything, but we can analytically predict, you know, what's likely to happen. And so that's the best we can do.
But it should, but who knows?
Well, yeah, I think it's a little, not quite that risky, but yes, it is. And it all depends on how good we are at hypothesizing what can go wrong and incorporating into the design of the system, whatever it is. That if that should go wrong, the system would be resilient, strong enough to withstand it. Even though we can't, we might not even be able to test it, you know. But
it's the unknown unknown.
It's unknown.
But how do you prevent those unknown unknown? How do you prepare for it?
Well, by definition, unknown, you can't, right? If you don't know what it is, right? You can only hypothesize what it might be. You don't know, and so you know you can say, well, it could be as bad as X, Y, or Z, and then you can synthesize an X, Y, Z environment on the ground that you could test it. But that X, Y, Z is just a guess, you know, and maybe it's not X, Y, Z, maybe it's X, Y, Q. And you didn't design for that. You didn't think of it. You know, it was unknown, and you know, now you're just taking a chance.
Could you simulate most of the environment inside JPL?
No, it's more like most of the environment inside my head.
Okay. So I was thinking that we have a magic chamber inside JPL. You can put in numbers and meters, and then you disappear.
Yeah.
Like in Hunger Games.
Yeah, exactly. Yeah.
Okay, so I think a lot of students ask about SpaceX.
Yes.
So what do you think the most difference or a different part comparing SpaceX to a giant organization like NASA JPL?
Okay. Well, first of all, SpaceX is run by one man, a very brilliant man, but just one person. And anything that comes up, you know, is of an idea to pursue it or not to pursue it, one man has to say yes, and it doesn't matter how many other people say no. You know, in NASA, it's just the opposite. You know, you can have 100 or 1,000 people saying yes, and only one guy has to say no. So the rate at which things can happen, I mean, in NASA, you have to study everything, you have to have everybody's opinion, you have to explore, you know, you have to prove that whatever you're doing is going to work. Elon Musk doesn't have to do that. You know, he likes the idea. He thinks it has, just looking at the basic physics, if there isn't any reason you can't say no, there's no way of it working, he'll say yes, let's try it. And then he's able to do things so quickly that he can try something, and if it doesn't work, you know, he just builds another one or flies another one. If you have a failure at NASA, you know, or even with the Air Force, I mean, we've got rockets that we launch, guided missiles, we launch spacecraft, we launch satellites, communication satellites. If one of them fails, there's a big investigation. You have to do it because you have to satisfy the political system that you haven't wasted the money, you know, that you didn't take any unreasonable chances, that you were prudent in every respect. Elon Musk doesn't have to do that. Elon Musk says, yeah, I see it didn't work, but I can. Yeah, that could be the reason. Let's build another one and try it right away. So he does something that is politically not possible with an organization that's funded with taxpayer money. You have to be accountable to the taxpayer. You have to convince the people in the political arena that not only what you did was reasonable, but it was the best that could have been done under the circumstances, and then you move forward from there. And that takes longer. I mean, Elon Musk, you might be able to guess at this, I'm a big fan of his. I really think he's done great things. But he managed to do in the course of 6 years what NASA wasn't able to do in 60 years. And so that's a big difference, and I think that's characteristic of why he's been as successful as he has. And he still could go bankrupt, you know. In the end, probably it's just like socialism, you know. It's a great idea until you run out of other people's money. Well, Elon Musk doesn't have anybody else's money. He's doing it on his own, which is one reason he's able to do things as fast as he has. I think he's great.
影片结束了。
好，刚刚那个影片就是我一开始的时候忘记稍微翻译一下了。我们一开始的几个问题，我第一个问了 John。I'm just doing some translate about the question I went through.
Okay.
You went through about aliens. 就是稍微简单的讲一下。第一个我问的是 John 他相不相信有外星人，然后 John 说当然是相信的，因为这宇宙很大嘛。然后所以在这个时间，在宇宙的某一个地方，有2个人正在面对这个一个教室这么多的人，然后正在讲这些事情。然后即使这样子的事情是完全有可能的，因为这宇宙真的是太大了，所以一定是会有外星人的。然后我问他了关于就是霍金之前不是有说我们应该要少去找外星人，因为这样子很危险嘛。然后问了他的想法，或者他那时候为什么要做一个小金盘这样子的东西，告诉外星人我们在哪里。然后他简单的回答是说，他不觉得会有什么危险，因为那个实在是太远了，他们实在是太远了。然后就像是我们现在去看一些以前古罗马的书，也不代表我们会遇到古罗马人嘛。然后但是我们会从这些文件资料里面学到一些东西，所以他会觉得像是 Voyager 就是 金唱片这种东西出去了以后，被某些东西捡到的时候，他们会知道说曾经有这样子一个种族，然后活在这个宇宙里面，他觉得是一个就是沉默的信使这种感觉。哎呀，之后你们自己再去多听，其实他的英文还蛮简单啦。然后我就问他为什么想要太空探险，然后太空探险就是最简单，就是因为人都是好奇的，都会想要知道。那因为想要知道，所以就有科学嘛，那科学又创造了科技，然后科技又 inspire 更多的科学，就是这样不停的 loop。然后又问他说，因为 Voyager 大家说是就最重要的一个太空的任务，然后他是不是最喜欢 Voyager？ 然后为什么 Voyager 最重要？然后他说的很像是，就你有很多小孩，你问他他最喜欢哪一个小孩，他很难跟你回答，可是他会觉得 Voyager 是很重要的一个，因为这真的就是第一次我们飞出太阳系，然后即使就是10年之后，就是 Voyager 没有电了，不能动了，它还是会一直在那边，然后也是在传达说我们曾经存在的这个事实。所以那个是之前的简单的一些翻译，之后的 Q&A 我也会尽量就是用我自己的话稍微简单拙劣的翻译一下，可是还是鼓励大家之后回去再看一下他的英文，其他的英文没有那么难。So I'm just doing some short translation about the question we did before because I forgot to translate. So that's moving on to the next one. So we talked about SpaceX.
Okay,
right?
SpaceX.
Yes. So how do you think private company like SpaceX will affect NASA JPL?
Well, NASA is a government agency. It's operated with money that is collected from taxpayers. And it's the dispensions of that money is determined by politicians, right?
Just talk about that in another question.
Okay. Wrong answer.
Just really focus on like how it will impact its impact on NASA JPL. Would you have like different direction of the mission because some part is covered by this private company, so you are into something else, or how it would affect?
Well, I guess maybe I was maybe not answering the question directly, but the main difference between a company like SpaceX or many of the private industries that are so active in space now is that they don't have to answer to anybody but the person who's running that company. In case of SpaceX, it's one person.
Do anything they want.
They can do what they want, and what NASA has done is laid a lot of groundwork over the past 50 years that's really made it possible for other companies to come in and do some things that if they had tried to do it from the beginning would have cost a lot more money than any one company could have possibly put together. But the government did that, and that's the difference between NASA and private industry. Not a good answer.
Let me translate. So 刚刚他讲的其实就是跟刚我们前一题讲的有一点点像，然后因为那个政府花的是大家的钱嘛，所以政府可以花很多钱很多时间把整个基础全部都打好，所以现在 private company 他们可以用自己的钱，然后在这个建立好的基础之上做更多其他的事情。
Okay, so just summarize what I was saying. In a private industry, it basically only takes one person to say yes. In government, it takes only takes one person to say no. You can have 100 yeses and one no with a government operation, and you're dead. In a private industry, you can have 100 no's and one yes, and you go. So that's the difference.
So they could have a lot of crazier idea in the private company.
Yeah, yes, they can have crazier ideas. Yes. I mean, look what NASA did. If I could just say, look what Elon Musk did in 6 years, launching spacecraft. He launches more spacecraft now than any country in the world, I think, in terms of frequency. Certainly a lot more than NASA does, and probably a lot more than NASA ever will be able to do. But he does it regularly, and he does it, and he's not afraid to fail. You know, he will keep going. So that's a big difference. Now, NASA's got to do things that are really high risk, high technology, that is maybe a little too risky for private industries to do. But eventually it'll get to the point where somebody in private industry will figure out how to make a lot of money doing it. Unless you can make money going into space, it's not sustainable, right? I mean, it's got to be science and technology, but at a certain point in time, you know, enough will be enough, and whether the amount of money that continues to go in there will only depend on what the return is, how much money will come back by doing it. And nobody's got to figure that out yet, but I think one of these days someone will. Yeah, maybe Jeff Bezos or Elon Musk.
I cannot remember everything you said. 但是简单来讲，他讲的就是 NASA 他们会更着重于在风险非常高，然后科技要求非常非常高，然后没有人做过的东西。然后因为那是大家的钱，然后如果要到私人公司的话，他们就可以在这些东西上面，因为 NASA 他们已经做过了，他们的风险会小一点，不然他们要花太多钱在里面了。然后他们可以用这些钱，然后把它变成商业化，然后之后可能可以用这些东西来赚钱。可是大致上是这种感觉。好，那我们继续下一个问题。Speaking about failure, so we have some question from a student saying like when you're in JPL, there will be a lot of high pressure time. And
Yeah.
there should be a lot of failure that you don't know how to deal with it, or some there's a roadblock. Now, how do you deal with high pressure? How do you deal with failure?
Well, first of all, you try not.
Fail.
We try to avoid failure. Well, it's you know, I manage several projects, and I think the thing that I felt about didn't answer that question. You know, if I didn't wake up morning being scared, I would think something was wrong. You know, then I would go out and try and figure out what's wrong. Why am I not worried? Yeah. And
他说他通常早上醒来了之后，让他醒来发现自己完全没有在担心任何东西的话，那一定是有哪里出错了，就是为什么没有在担心呢？所以他每天早上醒来都有在担心一些什么东西。
yeah, my wife used to tell me that I was the biggest pessimist in the world, and I'd say, "Why do you say that?" She says, "Because you're always trying to find what's going wrong." I said, "But that's not pessimistic, you know. That's a road to optimism, because if you can figure out what could go wrong before it goes wrong, then you have a chance of doing something about it." So I think a big part of our business in space, especially at JPL and NASA, is to try and anticipate everything that can go wrong before it does go wrong, and then take steps to the degree that you can to prevent those things from happening. So that's it, and you have to keep thinking that way. And if you can't live with that, then you should do something else, you know.
Okay. So let me do a translation. 刚刚这样说的是他之前他老婆都会说他这人是世界上最悲观的人，然后这样说这个才不是悲观，他只是他在往就是乐观的路上，应该是这样讲。他就是在所有东西可能出错之前，先找到什么东西会出错，然后阻止它出错，这样子就不会有出错的机会。然后他说大家都应该要这样子想，如果不可以做到这一点的话，就是防止找出所有可能出错的东西，不让东西出错。然后不能做到这一点的话，就是可能不适合做这件事情，你就是想办法做一些其他的事情就好了。Yeah, and so the mentality is to not fail.
The mentality is to not fail. That's right. Exactly right.
所以基本上就是怎么样面对失败，他的说法是不要失败，真的超 man 的，就是可以直接这样子讲。And we have another question about technology. So, what are some technology you like really wanted to have that you will be a good advantage or good advanced to the space industry? So what are some things that can be improved in terms of technology?
I think the biggest thing that we can introduce into space activities that will make the breakthrough, I mean, to make things possible to do that we cannot do now, would be the advent of nuclear power. fission power, not fusion power. Fusion power is something else, but fission power. It's the same kind of nuclear energy that we have in nuclear power plants all over the world today, and in submarines and aircraft carriers. That's fusion technology. NASA started out years ago working on that. They built, I think, 2 fusion-powered systems in the early 60s. JPL built, NASA built 2, but Russia launched, pardon?
Is it a Prometheus project?
Prometheus project. That was a project was started by NASA in the early 2002, I think. Yeah, and I was part of that. And I think that was Sean O'Keefe, who was the NASA administrator at the time, believed that, just what I said, that the next breakthrough in space exploration, whether it was human exploration or robotic exploration, will require the use of nuclear power. And he was committed to start something like that, and he did.
Why nuclear power? Like what? Why? Like does it?
Well, because it's.
Aren't we already use nuclear power now for all the robots?
For what?
For all the spacecraft.
No, what we're using is the Russians have launched about 30 nuclear fusion power systems, fission power systems. We launched 2 in the 60s, and then we went away from that. It was expensive, and the fuel was hard to get, et cetera, and there were safety issues and everything else with it. But we launched 30 or 40 of those, and since the early 60s, that's the only kind of nuclear power we've launched. It's not the kind of reactor power that we use on the Earth. It's something that works a lot simpler. It's reliable, but it's limited, and the fuel is very expensive, and there are safety risks in handling it all along.
So
the Russian,
expensive,
yes,
and still very hard to get.
Yes, yeah.
So it would be really nice if we can find a way to make it more handleable.
Well,
usable.
Well, yeah, the way you do that is by the reactors, the power supplies we have today are not reactors. They work by taking the radioactive decay of some nuclear material, which generates heat in the process of the decaying, and then take that heat and convert it to electricity. That's just like your gas range or your wall heater or your dryer has a little pilot light in there, and the pilot light warms up a thermoelectric material, and it generates a very low voltage, and that voltage can be used to open a solenoid valve that allows gas to flow, and then the gas can be used to heat.
没有啊，我只是听演讲而已。
What was that?
请所有的听众，麻烦你静音一下。
Let me translate.
Anyways, I was getting too complicated.
Let me translate.
But there's another.
Forget.
Okay.
所以我刚刚在问的是有什么样子的科技的进展，然后会帮助整个太空产业。然后这样是说核能，他说这个核能不是我们现在就是核电厂那种核能，是另外一种核能，更简单却又更复杂的核能。这到底是什么样子的解释呢？他说，俄罗斯之前 launch 了3个就是非常价值的核能，然后他们在60年代 ，NASA 在60年代的时候大概就 launch 了2个，然后后来又 launch 了一些，可是这种电就是非常难，然后又不是非常的安全，所以我们刚刚是在讨论说，就是所以是希望利用核能推进，然后让它可以更好用，还是怎么样？对。
Okay, so
nuclear power is a really nice advance.
Nuclear power. The way we use nuclear power in space, you can use it 2 ways. You can use it to generate electricity, which I very strongly endorse, or you can use it to generate propulsion capability. You can have nuclear thermal propulsion, or you can have nuclear electricity. Yeah. Accelerate, yeah.
所以核能可以有2种用法，第一种用法是可以拿来发电，然后第2种用法是可以，他刚刚说的那个词我忘记了，但是总之就是可以用来那个控制速度，可以拿来加速。
Yeah.
对。 听完最后名词就忘记。
Well, anyway, so John O'Keefe directed NASA to begin a nuclear electric propulsion capability. That was Prometheus. And there was a change in administration, and the next person that came in thought that the priority should be on nuclear thermal propulsion. And so all of the nuclear electric propulsion work that NASA and DOE and the Navy had been doing up to that point in time was certainly was terminated, was put on the back burner. And pardon?
Is that why?
Why?
Is that why? Like I saw the final report you put on together about Prometheus.
You did?
I didn't know it's because of change of executive level.
Oh yeah. Because the next guy that came in as the administrator of NASA was focused totally on Mars missions and putting humans on Mars, and he thought that nuclear thermal propulsion was a higher priority.
Okay.
And so everything got changed, and that's the way it stands today. NASA's still working on nuclear thermal propulsion, and
Sit closer to me because you're out of the frame. You'll take choose to translate. 他之前其实有一个 project 叫 Prometheus， 然后就是在做这个东西，然后做了好一阵子，然后后来是因为高层换人了，然后那个新的高层就觉得这个东西不太重要，就是看火星比较重要，所以这个 project 就稍微暂停了这样。
Yeah. So the NASA administrator at that time was believed that we needed to mount a big effort to go to Mars, which is already ongoing, and he wanted to accelerate that. That he thought that nuclear thermal propulsion would be a direct contributor to Mars exploration, whereas nuclear electric propulsion could come along later. So that changed the dynamic and everything. And today, NASA is not focused particularly on nuclear electric propulsion. They're thinking nuclear power for sustaining life on the moon and later on Mars can be a reason, but it's not the main focus that NASA's got. Not anymore.
Speaking of that, so one of the students is asking, so if you have a chance to change one of the design after Voyager, what would you like to do? Would that be the battery?
No, the battery? No.
If you got to change one thing of the Voyager design, what would you want to change? So not the battery, not the power system.
I don't know that we would change very much on Voyager. I mean, the technologies that we have today would allow things to be done somewhat better, but it wouldn't be any, I don't think, revolutionary change, no breakthrough change.
Interesting. 所以我刚刚问他是，这是一个你们之间一个人的问题，就是如果有一个东西它可以改变，就是关于怎么样 design Voyager 这个 spacecraft 这个太空船，它会改什么？我以为他会回答 battery 电，因为他刚刚花很多时间在讲电啊，怎么样可以 breakthrough。可是他说他不会改任何东西，因为现在的 technology 跟那个时候比起来，就是可能会有比较好的 performance，就是假设比如说画质可能高一点之类的东西，可是不会有任何东西是就是革命性的变好，所以整个的设计还是会是差不多的。Oh, that's interesting.
Well, that's the point that goes back to what Sean O'Keefe said. You know, until we get nuclear propulsion or nuclear fission capability in space, we're just going to be making incremental changes. There's not going to be any breakthrough, and that's where we are.
他说，直到他们 figure out， 我真的不知道 nuclear propulsion 的中文是什么，知道吗？邓凯？
就是原子能反应炉嘛。
原子能反应炉，就在那个东西我们可以好好使用之前，就整个太空船的设计啊，或者是太空探险这种东西都不会有任何的革命性的突破。直到我们
同学回应我们是说是热核发电。
热核发电。Oh, that one is helping us on the Mandarin term of nuclear propulsion.
What?
Because I don't know the Mandarin translation for that term, so someone is helping.
Okay.
Yeah. Okay, the next question is about, actually, would you like to talk about how you started?
How I started?
Yes, how do you start it to JPL? It's like your dream job or how do you start it?
Well, no, you know, growing up, I was a person who just liked to tinker with gadgets and stuff like that. But my family and everybody that I knew was in business and was interested in doing business things and not tinkering. So I never got any encouragement to tinker. I got, you know, so when I went to college, I went to the University of Pennsylvania and entered as a freshman in liberal arts. I studied liberal arts for 2 years. And then I had to choose a major at the end of my 2-year period, and I had choices like economics, you know, well, I was going to say socialism, but I don't mean that. You know, French literature, English, that sort of thing, and all of the history, geography.
Don't like it.
I didn't like it. I didn't like any of it. And so I asked my dad, could I go in the Air Force for a year or two and mature? And he turned me down. He said, no, you go back there and I don't want to see you again until you figured it out. So I talked to someone who was an electrical engineering student, and
he's a good friend of yours, right?
He wasn't a good friend of mine. He was a freshman and I was a sophomore, so I knew him, but and we were friends. But he was in electrical engineering. I didn't even know there was such a course you could take. So he said, well, why don't you come down and check out the electrical engineering department? So I did that. And they offered me I could come back the following year as a sophomore, provided I did certain things like summer school and then taken some extra courses in the next semester at the Drexel Institute of Technology, which was close by the University of Pennsylvania. And this guy says, this is great. He said, we'll be sophomores together next year and we can do homework and I can help you with the rough spots and all that stuff. So I went to summer school and he went home. And when the fall semester started, he didn't show up. I said, what happened to him? He said, he flunked his exams. We kicked him out. So I didn't have a friend to work with, but, you know, I managed to survive. And 3 years later, I had my degree in electrical engineering, and that's how it started. But I didn't plan it that way. It wasn't the result of any strategic intent on my part or any of the people who were guiding me at that time. They all wanted me to do something, but they didn't have any clue what it was.
所以他说他的家族里面大家都是文组的，全部都是文组，所以他那个时候进学校的时候，他其实也是文组生。然后，但是他在分科的时候，他有一大堆就是要选主修嘛，然后都是一些什么文学啊，什么就都很文，然后他不喜欢，他就是很不喜欢。所以那时候就想说，那他去空军去个几年回来，可能人就成熟了。然后这提议被他爸拒绝了，他爸说就是不准你跟我就是继续念书。然后那个时候有一个朋友。在一个学校里面，然后他那时候是念电机，然后他说他那时候甚至不知道有一个专业叫做电机，然后他朋友就说，这个很好，你可以过来看看，然后我们可以一起上学啊，一起怎么样，然后他就去考了一些试，然后就过了，然后后来就顺利入学了。可是那时候他朋友也不在，他朋友就被2-1了，那总之就被退学了。然后但是他倒是就是顺利毕业，所以他说他就是念电机啊这些，就是他没有什么任何的策略，他就是不是想好的，也没有任何的计划，也没有任何策略，他就这样子发生了。Then what brings you to JPL?
What brought me to JPL? Well, I came to California with a friend of mine another different friend. A guy that I knew very well was my very good friend in school at the university. He was a chemical engineer, and my degree was in electrical engineering. And we had had an interesting experience in our undergraduate years with a USC football team coming to Penn, and I think we got walloped pretty badly, but they had the best looking cheerleaders of any school we'd ever played against.
School in LA?
Yes.
Okay, so that's why you came.
That's why I came to LA.
Fair enough.
And so I
do this part first.
Okay. Okay.
那他那时候为什么会来 JPL？ 他一开始其实不住 ，Where are you from actually？
Philadelphia.
他原本在费城，然后他来加州，他来 LA 其实是因为他朋友。他们为什么会来 LA 呢？因为他那时候很喜欢看 football， 就美式足球。他说 LA 这边有一个学校的啦啦队超正，他们就因为这样子搬来 LA。这个 part 就是我要先翻译，然后 keep going。
So that's it. So I
came to LA.
I came to LA. I got a job interviewing at JPL with a man who was a very interesting guy. His wife was from Philadelphia, and so I think there was a little bit of a connection there. He was interested in me for that, maybe, but also because I think he liked me. I described things that I had done after I got out of Penn for a year working at the Rome Air Force Development Center. It was an Air Force Development Lab in upstate New York, and I'd done a couple of interesting projects there. And this man was very interested in what it was, and so he offered me a job. And I was living at that time in the fraternity house on the USC campus, and every day after I did the interview, he would send me a telegram or call on the payphone in the fraternity house there, and
you're comparing different offers at the time, right?
Yes, I was comparing different offers.
So is that why you choose JPL?
I chose JPL for two reasons. One, they said that I probably wouldn't be able to get a job there because I didn't have an advanced degree. I was only had a bachelor's degree, and they told me that most of the engineers up there were advanced degree. So they said it's not likely you'll get a job there. So that made me more interested than anything else. And then the other thing, the job offer was in Pasadena, and the other job offers I had were in other parts of Los Angeles, and I thought Pasadena would be a more interesting place to live. And my friend who I came out with had a job in Alhambra, which is not too far. So those were the two reasons I took the job.
So it's not like you have a long time journey without space.
Yeah. But that was dumb luck more than anything else.
我问他那个时候，他们因为啦啦队很正，来了 LA， 他就开始找工作嘛。然后问他说他那时候为什么选 JPL， 因为他那时候在比较几个不一样的 offer。然后他说第一个是别人说他超难进 JPL， 因为大部分进 JPL 的人通常都是要么硕士要么博士，大部分的人都是博士。然后所以他只有大学毕业，超难进。他就觉得说这么难进，那我就要进给你看。然后那是他的想法。然后第二个原因是因为 JPL 在 Pasadena， 然后其他的工作可能就是在其他地方的 LA。可是这个跟他一起来 LA 的那个朋友，就是的工作在 Pasadena 附近，超近。所以就因为这两个原因，他选了 JPL， 完全不是因为小时候有什么对于太空有什么梦想之类的。他说他只是就是他真的非常非常幸运。It was nice. It was quite interesting to hear you about that.
You think so?
A lot of students actually ask, like, have you ever, is that all you dream about, become an astronaut, get into aerospace, and how to get in? But it's like luck.
Yeah. In my case, it was luck. It was luck. And I don't advise anybody relying on luck for anything. You know, as a matter of fact, I think I told you once about
We have that in one of the clips. We're going to use that as a bonus clip.
Oh,
okay. 所以因为我们之前聊了太多天，聊了大概2个小时的天，所以有一段影片是他讲关于幸运，他觉得什么样子是幸运，我们之后可能会再把它放在网络上。但是总之他刚刚说他的 case 来说，他觉得他真的超级幸运，但是他不建议大家会只依靠幸运。对，然后刚刚这样。Let's move on to another question from another student. Oh, it's a follow-up of the radio question. So, they say we use radio to deliver the messages from spacecraft to Earth, but the distance in the radio will pass some planets or dust. Why the message not disappear? 就是我们从用那个 radio 从线讯号的时候，中间会有一大堆星辰啊，会有其他的星球啊， 可是为什么这个讯号不会消失？
Well, I'm not sure the message. Are you talking about the message that's on the record? Is that what the question?
Data.
Oh, the data.
So we send something from Earth to the spacecraft,
Right.
or the spacecraft back.
Yes.
On the way, there are a lot of planets or dust or something.
Yes. Yeah.
But why does it not?
Well, because the cross-sectional area of the planets is very small compared to the beam of the radio beam, so it only blocks a little small part of it. I mean, you look up in the sky and you see stars up there, right? And there's a lot of black space between the stars. There's not much there. There's nothing there to stop a radio signal. The radio signal passes right through.
Radio signal is like huge radio signal.
Yeah. Huge, the beam width of the radios. Yeah.
他说，那个如果我们看天空的时候，我们会看到星星，可是黑的地方比星星还多，所以它在 send radio 的时候会有东西被挡住，可是不会挡到那么多，所以大部分的 radio signal 还是会 go through， 大概是这个样子。That's easier than I thought. I thought I'm going to translate some hard technical thing.
Yes.
So,
Yeah,
another question.
I mean, that guy gave the wrong answer. Is that what you're saying?
Okay.
Okay.
So another question about project management. What is the most difficult responsibility as a project manager of a space mission? I think a lot of people actually ask this because a space mission is different than other mission. It ranges from a long time period. It's a long time period. A lot of people involved. Things are difficult,
Right.
and things are complex,
Yeah.
and there's no chance to fail.
Oh, there is a chance to fail.
And like, what are the most difficult or the biggest responsibility as a project manager?
I think maybe one of the most challenging things in any enterprise is communication, making sure that everybody who's working on the project is working to the same objectives and with the same priority. Everybody has a different idea about how to get something done, but in the end, you just have to choose one way.
How do you choose that?
Well, you ask questions and you solicit ideas from smart people, and you listen to everybody. And in the end, you have to make a decision. Maybe you have a couple of people that you particularly value their input or judgment on. But in the end, you have to pick one way. And having picked that way, you've got to convince everyone that we can't do everything. We have to pick a way. And the thing about it is there's more than one right way of doing everything, right? You can always find another way that'll work almost as well. The problem really is that there's a lot more wrong ways to do stuff than are right ways. And so you just have to pick one right way and go with that, because you can't do everything. You can't do them all, because each one takes different effort. So you have to make sure that everybody understands what the goal is, and and you lay out some priorities, things that we used to call them competing characteristics or certain aspects of the mission, that have to be valued more highly than the others. So the project management has to put those issues out there so everyone on the team knows what they are. And we want people to use those issues and that rank ordering as their prioritization for them to choose what they're going to do. And so then you need, go on.
That's the first part.刚刚的问题是，就是身为一个 space mission 的 project manager， 然后他是怎么样 manage 这些东西的，然后怎么样他的责任，我的中文也变差了，就是怎么样的责任有什么样子的责任啦。然后他说，第一个当然就是确定整个在 team 上面的人，大家的目标是一致的，然后大家的优先顺序是一致的。所以他说，大概做决定之前，他会问很多聪明的人，然后接下来自己必须要做个决定，因为你不可能所有都做，只能选一个。但是他说比较好的地方是，就是有 同样一件事情有很多正确的做法，但是有很多不正确的做法，所以你只要剔除那些不正确的做法，在这些很多正确的做法里面选一个就好了。然后接下来选完一个了之后，要就是说服大家，好，这就是我们的目标。然后接下来定出优先顺序。他说他在 project managing 的时候，他所有的东西都会有不同的 ranking， 就是不同的这个可能超级重要，这个不太重要，这个就是再不做就会死这种感觉。然后接下来整个 team 都要利用这种优先顺序来决定哪一个东西先做。Okay, so I'm talking about make sure everyone is on the goal and with the same goal and with your rank ordering, and then make sure we are choosing one right way to proceed, and then go on.
Well, you have to convince people that we all have to be playing on the same field, and we all have to know which end of the field the goalpost is on, and we all have to keep pushing in that one direction. And
make sure you are in the right direction.
Well, you can never be sure that you're in the absolutely right direction. You just have to be in a direction that's good enough. You know.
Yes, let's go back to what we said before. As long as it's good enough, it's okay.
Yeah.
And how to deal with if there's some conflict? Because it's a huge team, there should be some conflict between all those like JPL smart people.
Well, you cannot tolerate a whole lot of conflict because that's wasted effort. Conflict takes energy. You know, if you and I are going to fight, that we're using our resources, our energy, that doesn't produce anything, you know, except anger on both sides. We have to be pushing in the same direction, not pushing on each other.
And how do you do if there's a conflict?
You have to. It's communication. It's yes, yeah. I mean, people can be reasonable. I mean, if you ever, I remember I had a situation where I had a boss, and he wanted me to do something, and I thought, well, his name was Jack. I said, Jack, that's good, you know, but there's really a better way to do it. And I laid it out for him, and he listened to me, and he said, yes, I understand. I said, well, then I kept going. And he said, look, I understand what you're saying, but let's just try it my way. And the message was clear. If I wasn't going to do it his way, I was going to be out the door. You know? So
that's the one way to do it.
Yeah. But I mean, most people will, I think, respond. What most people want to know is what's the reason, what's the rationale, and you've got to be able to look at a situation, give them a rationale for why you want it done one way or another. Acknowledge that there's another way that would work, but we have to pick one way, and this is and I'm the boss, and you're not. So. But I mean, that can be done tactfully. You can't destroy people's initiative or desire to make things better. But that's another expression, I know, that we sort of try and teach people. And I think you mentioned it, at least alluded to it. And so the better is the enemy of the good. Making things better than they need to be, you know, is a waste of money. It only has to be good enough to meet the requirements of the job.
I'm not going to translate this part. They need to figure it out themselves. So, 我刚刚问他说，你刚刚说大家都有一样的目标嘛？那我就说啊，那么长的 project 你要怎么样确定就是你的团队在正确的 direction？ 他说没有办法确定是在正确的 direction， 只要是在还不错的 direction 就可以了。然后我就问他说，那这样大家可能会有很多，就是可能会吵架嘛，因为这么多人，这么多意见，那他要怎么样处理这些纷争或是不和？然后他是说，这个我觉得很有趣，他觉得吵架这件事情就是浪费时间，因为你要花很多精力跟时间去吵架，然后你得到的除了生气之外，没有任何产力，所以他说他不喜欢这样。然后碰到这种事情的时候，他就建议多沟通，就首先你先承认可能会有其他的做法，然后接下来大家想要知道的是为什么跟理由，你后面的逻辑是什么，然后让你的想法 What?
What?
Sorry, I was like listen in English and then talking. 你的想法就是好好的列点出来，然后这样子的话就有可能可以说服人家。然后当然是也有可能不可能说服人。他刚刚说了个关于 Jack 的故事。总之就是当他这样子已经好好的把所有的那个列点、原因都非常有逻辑的说出来了，对方还是可以 play。可是我是做决定的人啊，这个卡。那这个卡出来了之后，你还是要听，不然你可能就会失去这个工作。所以大致上都是这样子处理这些不合或是意见不合的。
Iris, just remind you 5 minutes.
Okay, 5 minutes. So we have last question. What do you want to? Which one should we pick?
I was thinking you wanted to do build a spacecraft. The most challenging ones. What is it? Most difficult thing you ever encountered in making a spacecraft, and how to solve it. That's number 7.
What is the most difficult thing you ever encountered in making spacecraft, and how did you solve it?
Gotcha this time.
I don't know if I can think of just one thing. We've run into a lot of difficult problems and that have to be solved. One example is that it was on the Galileo mission. We were building a spacecraft to go into orbit at Jupiter, which has a very intense radiation belt because it's got a huge magnetic field, and magnetic fields can trap electrons and other ions that emanate from the sun or come in as cosmic rays, and those particles go into orbit around the magnetic field lines, and the stronger the magnetic field lines, the more of those particles, and the faster they go, and the more intense the radiation environment is. So we knew starting out that Jupiter had a very large magnetic field. One spacecraft, a very elementary spacecraft, had flown by Jupiter and made a rough measurement of the radiation field, and so we thought we understood what it was. But then another spacecraft began suffering problems in another part of the solar system that we tracked down as being due to cosmic rays upsetting the internal aspects of integrated circuits to the point where a transistor could flip states, you know. And all of a sudden we realized that all of the electronics that we had already built and for this spacecraft were not going to work, and so, because of I'm saying that was a source of radiation belt. There was nothing we could do about that. Yeah, but no, the one we were worried about now were different than that. They were cosmic rays, you know, high energy ions, stuff that could come from outside the solar system. And
before Voyager.
This was after Voyager. After Voyager.
But why Voyager can survive with the cosmic rays, but not Galileo?
Because Voyager was using a more rudimentary form of electronics. We went to the technology. This is interesting because the old technology was not susceptible to the cosmic ray effect. But as the new technology moved on, the feature sizes of the transistors and the integrated circuits got smaller and smaller. This allowed them to operate quicker and with less power and was better all around, except for cosmic rays. And we didn't realize that that was a phenomenon that we had to deal with.
Until you find it out.
Yeah, and so we had all this equipment built, and all of a sudden we realized that it wasn't going to work, and so we had to do something different. And so there was another technology that was just being developed. It was called silicon on sapphire rather than silicon germanium, and there was one company that was had gone quite a ways with that, so we got a little contract with them to see if they could redesign all of our electronics that use the transistor logic, but we weren't sure that would work. So we went to Sandia, Los Alamos Laboratory, where they had been making circuits that were a entirely different technology that was not susceptible to cosmic rays. And we asked them if they could manufacture parts that could be substituted for the parts that we were using for Galileo. And they said yes, they could, and we funded them to do that. And they really did a very good job, and we were able to save the mission basically by using the parts that developed by Sandia. Now the problem was it cost a lot of money, and I was a project manager, and I tried to go find other people that were using the same part that we knew was going to be a problem for us, and to see if I couldn't get some support for funding the work. And everybody I talked to said no, they didn't want any part of it. So we went ahead and did it ourselves. And then when we got the part and it was working, people came back to me and they realized then that they had the same problem, and they wondered if we could sell them any of our parts. Yeah, so we sold some of the parts, but that was a nail biter. It was a real challenge from a schedule point of view, and it cost money too.
During the testing, right?
Pardon?
You get the issue during the testing. After you find out.
Well, it came to our attention because there had been 2 spacecraft that had been sent to Venus the year before and they were having problems, and we got with them and began to analyze it, and then we understood what it was, and then we said, well, the parts we have are not going to work. We've got to get to something else.
Okay, I think time is up, so I'm doing a quick translation on this, but this is interesting. 我们刚问的是，就是他在设计这些太空船的时候，有没有遇过什么超困难的事情？他说他在设计 Galileo 的时候，要飞去 Jupiter 嘛，木星。然后外面有很强的磁力，所以他们那个时候很多东西都设计 around 这个。就后来发现，他所有的电子产品都不能用。然后不是因为这些磁力，是因为宇宙射线。这宇宙射线，然后我就问他说：“哎，可是 Galileo 是在 Voyager 之后，为什么 Voyager OK，Galileo 不行？”然后他说：“因为科技进展了，所以他们用了一些新的那些线圈，它可能比较小，然后可以 save power。” 然后算的也比较快，所以他们换了新的做法，结果这新的东西反而没有办法抵抗宇宙射线。然后他们是在Galileo发射之前，他们在之前有飞一些东西去金星，金星那个时候就是用这个新的设计，然后就发现不行用，然后Galileo就有点，分析的时候发现是宇宙射线嘛，Galileo就有点来不及。然后他们就开始到处找，就是有没有人有旧的那个做法啊，还是有谁可以做出来旧的东西。然后搞了一阵子，然后好不容易弄出来，就后来就爆预算。也就是之后大家在听，我觉得他讲这个还蛮有趣的。但是这个我觉得是一个很好的例子，就是从前面的失败，然后学到什么东西可以改进，然后马上开始改进。Okay, I think it's time for today.
What?
And
Yeah.
What? It went fast.
Okay.
Okay.
You don't have any more movies to show?
No, maybe next time. Okay, 我觉得把那个话语权还给今天的主持人。
Okay, cool. Thank you. My special thanks go to Dr. John Casani and Iris. Thank you for very much for your great speech.
You're very welcome. It's my pleasure to be here. And with you, and with Don Kai.
As a well-known
And
entrepreneur,
Sahi.
what did he say? The 4 C's of your dream come true are curiosity, courage, consistency, and confidence. That are exactly we need for the space exploration. After John's speech, we have learned that universe exploration is an endless journey. That's why we have to keep going and always challenging ourselves. We continue challenging in learning and in our life. I strongly believe that everything is not over until we quit. everything is possible. Therefore, let us keep our passion with forces to create a world that is full of hope and peace. Okay.
Thank you.
Dr. John Casani, could you please give us a take-home message?
If there's one thing you want to say to the students, what that would be? Just one sentence or one message for them to take home today. If they forget everything you talk about today,
Don't ever give up.
don't ever give up.
Don't
不要
ever
放
give up.
弃。
是，好的。Thank you very much for your wonderful message. Now we have token of appreciation for Dr. John Casani and Iris. We would like to invite Dr. Liu to present the tokens. In addition, we would like to have Dr. Liu present awards to people who raise good questions.
Yeah, I'm going to give you some gift
Oh, you are?
for both of you.
Oh, okay, yeah.
We should. I don't know this one here is going to work or not.
I think he's going to give us a couple of airplane tickets that I pay.
That would nice.
I want to give to you, John. One is the student. This is a kit for the Voyager. And you built spacecraft before. You know how to put the kits together, right? Yeah, if you don't, you have the assistant here. Iris can do that.
That's great.
So that's the test here. And also I'll give you this ball here. That's
Oh.
Titan.
What?
That's Titan. Don't drop it. Don't drop Titan.
It's Titan.
The Titan, yeah.
Oh, what is this? This.
Put it on the stand. The thing will rotate. Remember you went to the neighbor's house? And this one put in here.
Oh.
The thing will be rotated because of the earth. No, the thing will be automatically rotated inside.
I don't know what
Once you get a power,
how do you power it?
then really get solar array, solar power.
Oh, okay.
Okay.
What about the heat from my hand?
And that will not work. Your magic hand is not going to work. Okay. So that's,
Thank you.
Whoa, cool.
that one.
Oh my God, look at that.
Rover.
That's
Yeah, that would be rover. Okay.
Yep.
That's a Perseverance rover.
This is the rover that's on Mars, the latest one, the last
Right
one.
now.
yes.
It's the one that carried the helicopter. Yes.
Okay. I want to express my appreciation here, John.
Well, thank you.
Yeah,
Thank you. I think the rover should be for Iris. I'll keep the ball.
The quiz ball here. Thank you, Iris.
So cool.
Yeah.
Look at this. It's starting to move.
Yeah.
I think I have one last question to John, for the student. So I know some of them are really interested in getting into aerospace
Yeah.
industry.
Yeah.
And do you have any advice for them? How do they start it? Or like, how do they get their foot in?
Well, I don't know what the opportunities for aerospace engineering might be in Taiwan.
Or like what knowledge or things they need to stress themselves?
Well, I think aerospace engineering, electrical engineering, computer science, all of those things are in very high demand. And then I think that if they're interested, there's always opportunities. I don't know what the universities in Taiwan have to offer, but there must be programs that.
Electronic engineering, computer science, aerospace engineering. These are the three things they at least need to.
I think there's, yeah, right, yes, yeah.
Actually, any field, even accounting would need that.
What?
Even accounting would need that. Yeah. Make sure we manage the project well.
Yeah. And if they ever want to come to the United States, we can always use bright, energetic.
You need a green card or citizen to work in the JPL, right?
That is correct.
It's a green card or citizen.
No, but if you have a green card, you'll be fine.
Yeah.
美国如果你要来 JPL 的话，至少要有绿卡，要
You
申
need to
请
prove
绿
that
卡
you're a resident there.
才能进 JPL。
Legal residence in the United States.
I don't know what the requirements are now, but most places have student programs, you know.
Right. Yeah.
JPL does certainly.
Right. Foreign students slightly different. Yeah.
Is that right?
Yeah.
Okay.
Okay.
Well,
Maybe
they should try Russia or India.
Yeah,
or
that
China.
would be good. They can try India, they can try Russia, or even Argentina. That would be a good program.
Yeah.
所以我们刚刚就讲说，来 JPL 做事情呢，可能你需要绿卡了，是这些东西，但是还有其他的国家，比如像阿根廷啦、印度啦，对吧？还有其他国家的话，都是很多的在这个太空方面做事情的。那我现在来宣布一下，我们的时间到了，我们来宣布一下这个得奖的，这个也是很困难的一件事情。我这个我们在这个事前得奖的有3个人，第一个是这个熊林海，是空军官校的。那有奖金1000块钱。第2名是这个潘启源，是大同的，媒体系的，那500块钱。第3名是邱秀泽，是300块钱。这些都是刚刚艾瑞斯在广播的时候都提到这些人的名字。然后这个在当场问问题的，第1名是这个陈金元，应该是在念中原大学的，就是他问他说这个Voyager 技术要改变什么东西的。那第2名的话是这个刘佑生，成大航太的，在建造这个太空船的时候最大的困难是什么？第3名是林建贤，是 Purdue University 的，对于一个 project manager 来讲，最困难的责任是什么？这是我们选出来的这个1、2、3。那我会送这个电子邮件给你们，希望你们在1个礼拜之后呢，帮我答复一下。那我电子邮件里面的话，可能要让你加入我一个就是 Line 的一个团体，那这样的话，我们这个把这个钱转给你比较方便一点。好，我就把我这个现在转给这个我们主持人。
好的，谢谢刘老师，恭喜以上得奖的同学们。如同我在演讲前开始所说的，我们非常鼓励同学们于活动开始前就上网查找资料，做预习的动作，提出自己的问题，希望同学们都能大胆提问，成就非凡未来。明年2022年3月18号星期五上午10点10分到11点45分，我们将开始新1年的演讲。同时，我们一直都很欢迎各位同学们加入我们工作团队，请扫描我背后的 QR code， 在表单中的问题区留下我要加入和你的联系资料，我们将会根据同学留下的资料主动联络你。参加这个志工活动呢，你将可以增进自我视野以及拓展领导能力。相当推荐各位同学在进入职场前就参与团队的运作作为职场体验，保证你受益良多，机会千万不要错过。感谢本次与会的各方学校各位同学们，希望大家都能在演讲中体悟到不同的见解，不仅从博士的演讲，亦从其他同学身上学到不一样的看法。再次感谢张卡萨尼博士与 Iris 为我们在座即将踏入社会的学子们提供丰富的知识、精彩的人生经验。最后，在这里要感谢本次活动中参与幕后筹备工作的师长同学们，首先是大同大学的何明果校长、许超云院长、包仓龙主任、陈伟杰老师、李尚林老师，还有与我们合作的陈一谦老师，以及本次宣传代表林同山同学。
嗨，
还有一大早不断的在跟各位确认设备的本次设备代表林信惠同学。
好。
远在新加坡为我们上字幕的 Justin， 还有为我们活动进行剪辑录影的佩轩，谢谢大家今天的参与，大胆提问，成就非凡未来。我们3月演讲再见，谢谢。